So we have talked about, the big gas laws, Boyle's law, Charles' law, Cayley-Sachs law. We talked about the combined gas law. Last time we talked about Avogadro's law, which is the relationship between the volume and the amount of a gas. And we have one more gas law that we're going to talk about here, and that is the ideal gas law. And our target here is to be able to use Avogadro's law and the ideal gas law in order to solve some problems. So let's go ahead and talk about the ideal gas law. The ideal gas law is a little bit different than some of the other gas laws that we've talked about so far. The other gas laws tell us about how a gas changes. Okay, there's a pressure 1 and there's a pressure 2. So it's the pressure before the change and the pressure after the change. The ideal gas law just tells us about a gas at a particular point in time. And the ideal gas law contains all the different gas variables that we've talked about so far. Okay, we've talked about pressure, we've talked about volume, we've talked about temperature, and we've talked about the amount in moles, right? And all 4 of these are part of the ideal gas law, as well as another factor that we'll talk about in a second here. It's called the ideal gas law because it assumes that a gas is ideal, okay? And what they mean by an ideal gas is that the particles of the gas are so small that as they bounce around, they don't collide with each other. That the only thing that they'll ever collide with is the sides of the container. And no gas is really actually like that, but just about every gas is pretty much like that. So the ideal gas law is actually a good approximation of how gases actually behave. Okay. Now, here's the ideal gas law. It says that the pressure times the volume equals N, the amount, times R, which we'll talk about in a second, times the temperature, right? So PV equals nRT. Okay, now obviously P for pressure, V for volume, N for amount, T for temperature, but what is this R? This R is what's called the gas constant, okay? And you can go and look up the R on the internet. You can look up the gas constant on the internet, and you will find several different amounts for this number, depending on what units you use to measure pressure, volume, and temperature, okay? N is always going to be in moles, but pressure could be in kPa, it could be in millimeters of mercury, it could be in lots of different things. Volume could be in liters or milliliters, temperature could be in Celsius or Kelvin, depending on what you use. That's, you'll have a different number for R. Okay, rather than learning what R is for any particular combination of units, I've kind of made a decision for the class that what we're going to do is we're going to use these specific units to measure our different variables in the gas laws. And then if we use these specific units, then R will be 8.3. Okay, so as long as our pressure is in kilopascals, our volume is in liters, our amount is in moles, and our temperature is in kelvins, R is 8.3. Okay. Now, if we have a problem and they give you a pressure that's not in kilopascals, you'll have to convert it. If they give you a volume that's not in liters, you'll have to convert it. If they give you a temperature that's not in kelvins, you'll have to convert it. But then you'll only have to remember one value for R. It's 8.3. If you go on the internet and try to look it up, there's lots of different values it could be depending on the units. But I've chosen this setup for us to use in class. Let's have an example of how to use this equation, okay? Our example, it says that how many moles of gas does it take to occupy 120 liters at a pressure of 2.3 atmospheres and a temperature of 340 kelvins? Okay, so let's go through and let's identify what each one of these numbers are. We'll make a list, and then we'll see if we need to convert anything. Okay, so it says that the pressure, it says 2.3 atmospheres. It says that let's see, it doesn't tell me a volume, does it? It does. It tells me 120 liters for the volume. That's the N, the number of moles. The question asks, how many moles? So that is the thing that we're looking for, okay? R, like we said, if all of our units are right, is 8.3. And then the temperature it gave me was 340 kelvins. 340 kelvins. Now let's look and make sure that all of our things are in the right units here, okay? So kelvins is right for temperature, liters is right for volume, but atmospheres is not right for pressure. So we're gonna have to convert this one. Let's come over here and convert those atmospheres into kilopascals, okay? So it says 2.3 atmospheres over 1. And if you look at the numbers that we used for converting pressures, on the bottom, I'm going to want to have 1 atmosphere. And on the top, I'm going to want to have 101.3 kilopascals. And if you don't remember those numbers, you can go and you can look back at that lesson. They were all there. Okay. Now I'm going to grab my calculator and I'm going to work this out. I've got 2.3 times 101.3, which means that 2.3 atmospheres is equal to, I'm rounding this off a little bit, 233 kPa, kilopascals. Okay. Let's put the problem back up there. Okay, now what I'm going to do is I'm going to take my numbers, I'm going to put them into the equation, and then we'll solve it. So pressure, we just said 233 kilopascals, times volume, which is 120, equals N, which we don't know, times R, which is 8.3, times T, which is 340. Okay. Now I'm going to take my calculator and I am going to simplify both sides of this. So here I'm going to do 233 times 120. And there I'm going to get some big numbers here. I got 27960. And on this side I'm going to do 8.3 times 340. I get 2822, and I also still have an N here. And then I will divide both sides by that 2,822 to get my answer. There I get about 9.9. Okay, and what units should we put on that? This is N, and N should be in moles. So it's 9.9 moles. There's my answer. So it's not too tough. You just have to make sure that your numbers that you use are in the right units. And if they're not, you'll need to convert. Let's have another example here. Okay, this one says, if I have a 50-liter container that holds 45 moles of gas at a temperature of 200 degrees Celsius, what's the pressure inside the container? So let's identify what they've told us. Okay, the pressure is what they asked us to find. Okay, the volume, it said it was a 50-liter container. So the volume is 50 liters. N, the number of moles, it tells me, it says it's 45 moles. R, as long as my units are correct, is 8.3. And then the temperature, the problem said 200 degrees Celsius. Okay, let's make sure that all of our units are right. Our pressure is what we're looking for. Our volume is in liters, which is good. Our N is in moles, good. And our temperature is in Celsius, but we want it to be in kelvins. So you remember, it's really easy to change to kelvins. We're just going to add 273. That'll give us 473 kelvins. Okay. Now everything's in the right units. Let's put these numbers into the ideal gas law and we'll work out what the answer is here. So pressure times volume. So pressure, I don't know. I'm just going to write P. And the volume was 50 equals N, which is 45, times R, which is 8.3, times T, which we said 473. Okay. Now we're going to simplify this and then we'll solve it. So P times 50, I'm going to write 50P. And then I'm going to grab my calculator. I'm going to multiply out this side. Let's see what that is. I got 45 times 8.3 times 473. And that's a big number. I get 17666. And I rounded that off a little bit. And then we'll divide both sides by that 50. So dividing by 50, my pressure comes out to 3,533. And what units should that be for the pressure? We said that the units that we're going to use are kPa. Okay, so there we go. Not too tough. So there is the last one of our gas laws that we're going to talk about, the ideal gas law. So now we've talked about Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law, Avogadro's law, and the ideal gas law. So hopefully that helps us be able to use Avogadro's law and the ideal gas law to solve some problems. Till next time, take it easy.